So we ended up last time talking about the fact that you have different kinds of metals in different kinds of organs with different kinds of biological functions. There's a connection between what the chemical can do and what the organ can do. And you know, there's lots of overlap between these functions. There's lots of overlap between organs. And so you got to realize this is a big picture way of looking at things. And yet the big picture makes sense, not just on the sense of, oh, we happen to have these metals and we happen to have these functions, and it's like shuffling a deck and you end up with a metal for a function and things like that. It looks like, and R.J.P. Williams' argument is, that these metals have particular characteristics that caused them to be selected. Because honestly, you have about a couple dozen metals that you could have selected. Why do we always see iron being used this way, with the occasional exception of copper being used for oxygen transport? You know, we can talk about the exceptions too. One of the things that I did, actually I was presenting once at a conference, and the next person got up and he was talking about rare earth metals, and he's like, yeah, that was a really interesting talk right before mine, but you know, there's this one example where this one enzyme uses a different metal to do the same thing. And I'm like, yeah, that's one enzyme though. We're talking about what do 90% of the enzymes do. And so scientists like to focus in on my particular area, my particular example. And this is more of a big picture kind of thing. And honestly, I never would have been able to see this. It took R.J.P. Williams to be able to see this big picture kind of thing. So the basic chemical thing that he connects these things to, we've talked about stickiness. And that is an equilibrium discussion of how tight something bounds. But you also know from your Biocor experience that it's not just how tight it binds, there also can be differences in how fast it binds. And so it's not just stickiness or the K value of binding of the element or the ion to its ligand. It's about the K on and the K off of binding as well. It's a really simple binding equation. This is A plus B goes to A slash B, or A dash B, you know. It's just two things coming together, but you know that those rate constants are going to be on the orders of order of magnitude kind of differences between the rate constants are what really matter. And you can see there are order of magnitude differences between the different ions, how fast things bind to them, and this is how fast anything binds, you know. You have nitrogen can bind, oxygen can bind. Whatever binds to it, it's usually negatively charged because these things are usually positively charged. But you have the plus-minus interaction. How fast is this in water? And so, for instance, sodium, potassium, and chloride, they bind really quickly with K-ons greater than 10 to the 9th. But their K-offs are also about 10 to the 7th or greater. So really big K on, really big K off. The big K, the equilibrium constant, is found by taking the ratio of the two little k's. And if you compare the ratio of these two things, yeah, you end up with a K that is more products and reactants. You end up with but it's only a little more products and reactants. It's only like a 100 to 1 ratio, even at equilibrium. And so that means that these things are really fast, but they also are really fast off. Really fast on and really fast off goes together. Calcium, on the other hand, has about as fast of an on as those top elements, but partially because it has two charges that help it hold on to the negatively charged thing more. In general, its K-off is going to be much, much lower by about 4 orders of magnitude. Because of where the K-off is in the fraction that gives you the big K, the K-off ends up giving you a big K that is 10 to the 6th. So calcium will actually be slower off. And if you look at zinc, zinc is one more down the road. It's almost as fast on, but it is super slow off, and that ends up with a large K. This is why we call zinc sticky, because a 10 to the 10th equilibrium binding constant is really big. And so we can say K equals 10 to the 10th, and chemists will understand what we do, but if we're talking to other people, it's good to use words like it's sticky, you know? So you have these kind of relationships, and if you follow this all the way through, you can see that he's following the right rules. Big K equals little k over little k. And in fact, a big K equals K on over K off. That's for the binding reaction. Same rules that we follow. And he even goes to other ones as well, but you can look up and down here, and you can see that there's nothing that is really as fast on and as fast off, and sometimes you want fast on and fast off. because you want to be able to turn off the signal as quickly, or binding event, as quickly as you turn it on. So I deliberately made this one slow. You have to wait for it. If you look at magnesium, it is much slower than calcium, and its K-off is actually 10 to the second as well. So you end up with a weaker binding. So you still see magnesium binding, but you don't see it being used for as many of the same things as calcium. One interesting thing is, I talk about calcium a lot and its role in signaling as the divalent ion, as its special role that it can do. And that is really prevalent that way. But there are some branches of the immune system that use magnesium. It's kind of like they want the second best, because the first best is already occupied. They want to send a slightly different signal. And so they can use magnesium, and it works okay for them. Zinc is also used for the same purpose in some cases by the synapses. So zinc is used like calcium, but again, only in specialized places, only in advanced organisms in the case of zinc. Copper has a fine K-on, so you're like, well, what's the problem? Well, you look over at the K-off, and it ends up with that super sticky K, 10 to the 15th, because it never comes off. 10 to the minus 7th come off per second. That is, it never lets go. You have to pry it off. And so it's not good for sending a signal that you need to turn off, at least that you need to turn off by letting it fall off by itself. This data was actually turned into this graph that was in A World from Dust. And I kind of like this graph. It's kind of unusual, but it shows, if you look at the numbers are very similar. And it shows that fast on, fast off, if you're looking for the speed master elements, sodium, potassium, and chloride are all way over here. So if you didn't have that last one, you could actually take this data and you could actually calculate the big K from estimating the little k's for each of these. Or you can just look at the graph and get a feel for it. Part of the reason for this is the charge of each of these elements, the size of each of these elements, that's set by the periodic table, and also their behavior in water. Because of the charge and size and the orbitals and all that, these will have slightly different behaviors with the shell of waters that's right around each of the ions. And it turns out that water exchange, so when the ion's here, it has a shell of waters around it. And the question is, how quickly does a water come in from the outside and sort of shove its way in and push another water off, okay? You can actually test this if you use D2O instead of H2O. And you can get a feel for how fast does water exchange on and off. Part of the reason why these are so fast is that water exchanges on and off really fast. Magnesium is slower because it's slower for water to get in. And if water's slower getting on, anything is going to be slower binding. These things are all related. I just want to say these are not some kind of esoteric measurement. It's just kind of how fast does something stick to it. So another interesting thing is that copper and zinc can still be used. You just have to use them for slow processes. So like adolescence. You want to talk about a slow, complex process, okay? You've got the development of the organism. You've got multiple years in which the organs are communicating to each other. And of course, what do we attribute adolescence to? We talk about the hormones, okay? And those are very slow working because they work on the scale of years. And that's why you can use pretty much anything you want. It doesn't matter how fast it is to make the hormone because the hormone works slowly anyway. So you can make something that has a bunch of covalent bonds and you can piece it together. You can convert cholesterol. You can do all that stuff. And so down here at the bottom, you see all of these hormone-related organs make these hormones. And they can use whatever they want. They still tend to use recent examples. You see copper, you see zinc, and you see iodine, which is actually a recent chemical as well. It's just used for only one purpose here. But it is for a hormonal kind of purpose, a slow purpose that you have. But you see up on the top, for nerves, brains need to be a lot faster than glands, okay? So the hormones, the brain uses hormones only for sort of short-term kind of projects, or it can make a bunch of certain neurotransmitters and store them up. But for the most part, for at least how the average neuron works, you're going to need to use something faster. You don't want to have hormones being the way that a neuron actually works inside itself. You want that to be as fast as possible because then you'll have a fast brain. And that leads to the DIY neuron, okay? This is a story about how a chemist can replicate what a neuron does by making something that's not really a neuron at all, but they're able to put it together. So the brain is a really specialized organ when you look at it. You need fast nerves to respond to the environment. There's sort of an arms race. You know, if the predator has fast nerves, then the prey needs fast nerves to run away. And the faster those nerves are, the better for the prey. Better for the predator, too. So the system is probably going to converge on the fastest possible ionic signaling that you can get. That's available as well. So fast nerves run on fast ions. And so you have sodium, potassium, and chloride that all have a fast role. And then you have calcium that's sort of a special different role. Now, what do we compare brains to say brain is fast? Faster than what? Brain is how an organism responds to the environment. The next best thing for how an organism responds to the environment is DNA change through evolution. But this is covalent bonds. This is tons of bases being replicated. This is organisms living and dying. It is literally a system built on death, because the survival of the fittest is how the information is passed on, okay? So before brains, you would say that the information storage organ was DNA, and that's a polymer of 4 bases. So DNA is not only slow, it's also clunky in that it can only store a little bit of data. You have to store it in bases that are 4. It's one of the reasons why it's so long, is that you can only store so much information in each base. You only have 4 choices, and that's what the bases convey. In brains, you don't have them running on bases anymore. You have them running on ions, but it's not really the nature of the ion, it's the location of the ion. And so you have a location-based kind of system. You have 20 different ions and neurotransmitters that are either going between the synapses or helping the synapses move along. And there's gradients of concentration. It's not just is the ion there or not, like it is in a base. It's how much of the ion is there and how quickly is it moving. So if you just look at the way information is encoded in the organism from the environment, you would pick a brain every time. Of course, brains are incredibly more complex. So I have this. This is a flash animation, and things have actually changed. I'm going to try really fast because I know I got this working in biochem, so it did actually work on this computer. And I just have to remember exactly when I did this. There should be, it's not a PDF. Yeah. I think I might just let you imagine it. What did I do with it? The thing is, I know it's actually in the history of this, but I don't see. Oh, you know what? I might have put it in. It was my brain talk, and I talked about that. Was it structural immunology where I talked about that? No. Oh well. I intended to look at this when I was going on this earlier. I'm just going to try one more thing. And we're just going to look at movies. Okay. Well, it probably won't run because it doesn't have flash anyways. And I can show you the same kind of thing. I have an animation for this that I show. Oh, I know I put it on chapter 12. I remember where I put it. Okay, let's try to see it. I'm just going to see real fast if I can find it. It should be right here. Okay, this is going to be crazy, but I'm going to actually, I should be able to find it here, because I gave myself little notes about where to find it. That's how this is related to how anesthetics work and things like that. Here we go. 4362, neuron propagation animation. So send yourself little notes. You never know when it will actually help. Okay, so and now I don't see it here. There we are. Oh, it's a whole folder. Okay. All right. Now let's see how this works. Hopefully it won't. Oh, now it's not. Oh, this is Edge. Trying to do the stuff, they made it in Flash, and now everybody hates Flash because you can, like, you know, take over someone else's computer with it. There we go. Okay, it actually works. And I made it go away. Okay. Here it is. Here is the neuron, and this is the version of that same graph that was in there. And I just want you to see how it works. Sodium channels open, they let sodium in, positive charge comes in. Later, potassium channels open, they let the potassium out. The potassium is slower. I think the potassium itself might move a little more slowly, but more importantly, its channel is just more complicated, and so it just opens more slowly. So it lets the sodium comes in and lets the positive charge in, and a cloud of positive charge enters. The potassium ones open more slowly, and they let the charge out. That's how you have a wave of positive charge moving down, and the positive charge affects the whole neuron. It affects the structure of all the proteins in it, and that makes the whole protein change shape, and it changes shape in a particular direction because the fast stuff is letting it in and it moves down the neuron. The slow stuff lets it out, but they're too slow to catch up to the fast stuff at the front. So you end up with a pulse that moves down the neuron, and the most important thing is down here we have a typo. We have a typo because down here we have calcium. These yellow ones are calcium charges, and you see you have the bubbles moving. The bubbles are full of neurotransmitters. Sodium is not strong enough to do this last step down here, okay? So you end up with calcium being strong because it has the 2+, because it has that slower off. It is able to stick around longer and push those bubbles around. So you end up with the whole system working. You need sodium, potassium, and calcium. Chloride plays a similar role to sodium and potassium, but it sort of like subtracts from the positive charge rather than adding to it. We're honestly still figuring out how chloride channels exactly work with all this. That's what I was trying to get across with this, and I think it's cool how Gala Bent translated it. The main thing is you have an arrow. Neurotransmitters come in. A charged wave moves this way. Neurotransmitters come out. You have unidirectional flow, which is really hard to do with chemistry. It's hard to have, you know, you can add a drop in, you can have it all poof out, but entropy takes over, right? The entropy is constrained by the whole nature of the system, including the cell membrane and the ion channels. Okay, so that's a really fancy way to make a wire, to make a charge travel in one dimension in a particular direction. And remember, force times distance, that's work. It's to make a charge do work for you. It's a lot easier to make a wire out of metal, but metal doesn't evolve. You know, metal only isn't liquid. It doesn't evolve through chemistry. Metal is not going to work on this planet for life. But can we go into the lab now, and can we make a fake neuron out of metal? One that will actually take a signal from one end, a neurotransmitter signal, and it will spit out a neurotransmitter signal from the other end. And in between, you have charge moving in a certain direction. The only difference is, in the middle, you know, to the other neurons, it looks like a neuron. But in the middle, you have the charge moving through metal. So you have the metal neuron is the way that this is made. And this is what this group did. For today, to finish out the data talk, we have 2 papers that I'm going to be able to ask you questions about on the test itself. Each of these papers has a particular PChem concept that you want to look at. So this one has the concepts of volts and currents and moving charge in a particular direction. Also, the interesting thing of how do you compare chapter 5, voltages, to everything else that goes on. So look at what they did. The fundamental function of neurons is you're taking a chemical signal, you're turning it to an electrical signal, at the other end you make another chemical signal. And then you snap all the neurons together, and There's a lot more to what's going on in the brain, but that's the basis of what's going on in at least a slime mold kind of brain. Well, slime molds don't have brains, but you get the idea, you know, sponge brain. So the biosensors will actually take these chemical signals, so we can make a biosensor that does this. It's just that the electric current is carried through a wire instead, all right? And so they made something that did this. It acted like a neuron because you can give it a physiologically relevant concentration of neurotransmitters at one end, and it will put out a physiologically relevant change in transmitters at the other end. In the middle, it doesn't look anything like a neuron, other than that it's long and skinny, okay? This is what they did. So this is the neuron, and we're talking about transmitting a signal along the length here. And you have a biosensor, which actually they bought. I'll show you the catalog pages for these. You can go on and buy biosensors. It's an electrode that you stick into a solution, and it creates a voltage when it has that particular molecule in solution. What does he use it for, exactly? Yeah, it's probably exactly the same thing. Do you know what chemical he's measuring? Because there's a number of different ones. Okay. Yeah, or that. The thing is, you can make it for anything, you know, and they make one for glutamate or acetylcholine, which are both neurotransmitters. And so you take an appropriate biosensor that receives the chemical signal, you transmit the signal through the wire, and at the other end you have an ion pump. Instead of vesicles, you have an ion pump. You load it with whatever you want it to spit out. And so in this case, they loaded it first with protons, and then they loaded it with acetylcholine. And that was their whole strategy. I just want to show you what they showed. When you go up and down, they talked about the different reactions that they do. And when they talked about these reactions, what do you see? You see that it's, you see the half reaction, for example, of H2O2 producing electrons. This is written in the oxidation direction, but other than that, this is exactly like what you are working with in Chapter 5. And really, this reaction is the same, whatever the biological or chemical context. So you see right here that they bought a glutamate sensor, and then they bought an acetylcholine sensor. And both of these, you don't even have to know how they work, but I want to show you how they work because these are something that you might use, like with Dr. Ridgway or something like that. Although you don't really have to know, you just stick it in the solution and it sort of goes. But you have to know when it troubleshoots, when stuff goes wrong, as stuff will. This is kind of what it looks like, this particular one. And actually, I made a slight mistake here. This is a glucose sensor. They actually had a glutamate sensor. You see, I messed up GLU for GLC. But this shows you the general principle, at the very least, that you have glucose coming in. And actually, come to think of it, it might be glucose. Let's see. Here we go. Let's see if it's glucose or not. I don't have it right here. I'd have to look at the paper. The principle is the same, whether it's glucose or glutamate, because the thing that's really making it work is you have an enzyme. The enzyme's providing the specificity. What is the enzyme making that is actually interacting with the electrode? Can you see from that? The enzyme takes in the glucose in this case. It's glucose oxidase, so it oxidizes it. What do you see? Yeah, it makes peroxide. Basically, it's messing around with the electrons, and it puts the electrons on water to make, or some kind of, it could be like OH hydroxide or something like that. Whatever it does, it takes some form of water, and it puts the electrons on it, and that makes H2O2, which has a very distinct half reaction. And that half reaction can be, those electrons can be pulled off of that at a particular voltage by the biosensor itself. And so that's how you convert glucose to an electrical signal. You have to use an enzyme. There might be other ways that, so I'm assuming that the biosensors usually use enzymes. I think there are occasionally other ways to achieve this specificity without it. For example, a pH meter is kind of a non-specific biosensor technically, but these kind of things, for a complicated molecule, you probably need an enzyme. here is the acetylcholine sensor, and they're just showing you this one. Just notice that you have platinum wire, that's an inert wire, it carries electrons, or their iridium for some reason works, or they can even use carbon fiber. That's electrical for the electricians to worry about. But you see right here, this also has an enzyme layer. The enzyme layer will actually take the acetylcholine and convert it to choline and acetate, and then you have an oxidase, again, that produces H2O2. The H2O2 is reactive. Did you all ever have parents who would, like, you know, when you got a cut, that they would pour the peroxide on it, okay? The peroxide bubbles, and do you remember anything about the bottle of peroxide that you used? Yeah. So definitely you had the pain reaction going on, right? And that's actually ions, because those are neurons responding to ions, and so it's actually related to all this. But the main thing is, how can you tell that a peroxide is an especially reactive kind of element? Because it had a special bottle, at least the ones that what's that? Yeah, they usually have that kind of brown. Yeah. Yeah, and that's to keep it, if you store it in a glass bottle, it would actually produce gas, and it would explode, you know, so that's not a good idea. But because it bubbles out, that bubbling is a sign of its reactivity. Because of its reactivity, it gives off its electrons fairly easily, and so the biosensor can sensitively measure how many electrons there are there. Okay? This is their data. So they actually first off started with a glue biosensor that would take either glutamate or glucose, and again, we don't have that exactly. I think it's glutamate, though, because that would be the proper thing. I don't think they would get that wrong the whole way. So we're going to say glutamate. They add a glutamate, and what they do is they have it sensed over here, produces a current, and that current causes the ion pump to release protons, and they just put a pH indicator here. So from the pH indicator, they watch the pH indicator change, and they watch the pH go down. They push glutamate into this dish, and the pH goes down in that dish. So it looks like we've created a artificial neuron, right? Then they did it with acetylcholine in each dish. So the acetylcholine sensor produces electrons, but in this other dish, look what they have. They have these little neurons. This is how chemists draw neurons, okay? It's not very accurate. They're kind of like green fried eggs, okay? But the thing that you did with this is you added some sort of fluorescent marker that would actually fluoresce when the acetylcholine was released. So acetylcholine comes in here, and you're measuring, actually, they're fluorescing in response to calcium. So that's the other connection to this lecture. The calcium is the very last signal that's sent, and they're actually able, I think they're detecting the calcium in the cells itself, so that they're detecting that last event. And they see the calcium go up, you put acetylcholine in here, and these neurons respond just like this is a neuron. You're fooling them into thinking that that's a neuron. And then can you connect two neurons in the same dish? And so they did that. They did that with the glutamate form because you can't have two acetylcholines in the same dish. But the glutamate turned into an acetylcholine signal, and it produced the same calcium response. That's really cool. So I posted this on Facebook. Oh, yeah, Angelina. Right. Okay. I guess your guess is as good as mine, but I think that that's probably pretty close to the truth. I mean, they were probably worried because it sounded like we could make robot brains out of these. And, you know, if we had the right number of these and the right kind of connections. Okay, so help me respond to my friend. Why shouldn't we be worried about artificial neurons forming robot brains and taking over the world like Skynet will or something like that, okay? Why shouldn't we be worried as it first seems when we say we've made an artificial neuron? Wait, Susie.
Just on like the basic idea, we don't actually know how they work 100% in our brains. We can't replicate it. We know how other brains do it.
Yeah, so the fact of even a single neuron has multiple connections, branches, you know, this doesn't even account for that. That's like having the 2-brick Lego, you know, and then having this Hogwarts castle that's life-size compared to it. I mean, that's probably about the order of magnitude of the complexity difference that we have. But Angelina, what would you say? Mm-hmm. Yeah. Yeah. And for each link, I mean, this is really big relative to what a neuron is, and not very, it is as sensitive as a single neuron. That's what they're really proud of. But the sensitivity was the only thing they were going for. They weren't going for size. They weren't going for cost efficiency. One of the big things to go is just how many neurons there are in the brain. A lot of people see this and they imagine, oh, I get 100 of these together and I have a robot that's going to beat me at chess, okay? Brains don't work that way. Also, you know, plasticity, gradients, a lot of the things that we can talk about, the brain, we're still figuring it out. And remember that we don't even know exactly what the difference is between chlorides as a signal and potassium as a signal. And yet, I think that there's just a whole lot to learn about the brain. So this is a binary event, and we really have all those a lot of other things to worry about. I'm not particularly worried about robot brains from that.